In this lecture, we're going to look at one of the frequent properties that one sees in fractals, and that's self-similarity. So roughly speaking, we say that an object is self-similar if it looks the same at all magnifications. Now, to say this more carefully, we're going to go back and review two notions from geometry. To understand what self-similar means, well, we should understand first of all what it means for two objects to be similar. And that may not be a familiar notion, but certainly I think from plane geometry you remember the idea of congruence. So we're going to start at that point with congruence. So recall that in geometry two figures are said to be congruent if there is a rigid motion taking one to the other. That is to say, informally, they are the same size and shape. Now, over on the right, I've illustrated this by drawing some kind of a blob. And then, just to distinguish it by a different color, I've drawn the same blob again. You can see it's the same blob. It's the same size and shape. The only difference between the two is where they're located. We would say that the blue blob is obtained from that maroon blob by translation, by moving it a certain distance and direction upward to the right. These two stars are also congruent. Now here, the rigid motion taking one to another is a bit more than just translation. We've also had to rotate, but you know you could take the blue star shown on the left and you could move it over to the right and then rotate it by a correct amount, and it would turn into the blue star on the right. Again, the stars are the same size and the same shape. They are congruent. Here's yet another example, a reflection of a key across an axis. Now we're going to study this kind of thing in rather more care and rather more detail at the beginning of our unit on symmetry. But this shows that a reflection across an axis is a rigid motion. It takes the key on the left to the key on the right, and one can say exactly how that reflection operates in a very precise way by taking points from the key on the left and giving you points of the key on the right. We'll look at this diagram again in a future part of the course. Now, what is similarity? Well, similarity is as follows. We say that two figures are similar if one is a scaled up or scaled down version of the other. In other words, when we're working with similarity, we're allowed to use not only rigid motions, but also expansions and contractions that change the size of the object, that make it larger and make it smaller. Similar figures have the same shape, but they're not necessarily of the same size. They could be different sizes. So the two blue stars I'm showing you here are said to be similar. The one on the right, obviously a scaled down version of the one on the left, which has also been translated and rotated to get to that position on the right. In plane geometry, one learns something about similarity. One learns, for example, that two triangles are similar if and only if they have the same angles. So here are two triangles, and they each have angles of 40 degrees, 60 degrees, and 80 degrees. And that means, in fact, that they have to be similar triangles. One is a scaled up version of the other. If two triangles are similar, as we've said, then the side lengths of one triangle are a certain multiple of the side lengths of the other triangle. I've given you a little example down below, and deliberately, so that you can see it doesn't matter how they're positioned or how they're oriented, that these two are similar triangles. That is to say, I could take the smaller one, the one whose side lengths are 3, 4, and 5, and I could move it over to the right and rotate it and then finally expand it so that it became a triangle whose side lengths were 6 and 8 and 10. Now, if we're concerned with that scaling part of the operation, never mind the translation and the rotation, but just simply the expansion or the scaling, what we've done is to scale by a factor of 2. That is to say, all the side lengths have been multiplied by 2. Now, we say that a figure has exact self-similarity if it is composed of several pieces, each of which is similar to the entire figure. Now, you probably never thought about this notion before, but in fact, some very familiar and simple geometric objects are exactly self-similar. For example, suppose you take a solid square. So I mean, take a square and fill it in with ink. Well, it's composed, if you like, of 4 smaller solid squares. That is to say that you could carve it up into 4 pieces, red, blue, yellow, and green, each of which was itself a solid square, and each of which is half the size of the original. A line segment, as shown here, is self-similar. That is to say, it is composed of 2 pieces, a left half and a right half, each of which is a half-scale copy. The Cantor set is also self-similar. What I'm saying is, when you look at the Cantor set, you can see that it has a piece on the left and a piece on the right. And each of those pieces, when we look at it, is just a copy of the Cantor set, scaled down. It's a 1/3 scale copy of the entire Cantor set. To say this another way, if we zoom in on the Cantor set, if we only pay attention to the piece on the left and we zoom in on that, we're still looking at an exact but smaller copy of the entire set. Now, let's compare what we said about the line segment to what we said about the Cantor set. In fact, let me go back. The line segment, we said, was composed of 2 pieces, each of which is a half-scale copy. But regarding the Cantor set, we said it was composed of 2 pieces, each of which is exactly a 1/3 scale copy of the entire set. So let me just have you ponder this for a moment. Again, the line segment is composed of 2 pieces, each of which is a 1/2 scale copy of itself. The Cantor set is also composed of 2 pieces, each of which is a copy of itself, but now these are 1/3 scale copies. They're only 1/3 the size of the original. We can make similar remarks about other familiar fractals. Here's the Sierpinski gasket, and when you look at the Sierpinski gasket, it probably seems immediate to you. It just jumps out at you that, in fact, the Sierpinski gasket is made of 3 smaller Sierpinski gaskets. You see there's the big triangular hole in the middle, and then there's a little Sierpinski gasket on top, and a little Sierpinski gasket at bottom left, and another Sierpinski gasket at bottom right. 3 copies of the Sierpinski gasket can be shoved together so as to make the entire Sierpinski gasket. Now let's do our counting and scaling again. We're seeing that the Sierpinski gasket is composed of 3 pieces, and each of those pieces is a 1/2 scale copy of the whole thing. Let's look again at this Sierpinski pyramid, and I'm showing you again the photograph of that model. Here we see that it's composed of 4 pieces, each of which is a 1/2 scale copy of itself. Now, to finish off this lecture, I want to recommend that you go look at a video. We've been talking about a little bit of numerology here, how we would talk about scaling and number of copies and so on. But if you really want to get the idea of self-similarity, a video is very helpful. So I want you to go look for that video, which is among the course materials, and it shows you how it feels to be zooming in on the Koch curve. So you're looking at the Koch curve, and then it's as if you're flying in towards it or you're enlarging it, and suddenly at some point it looks like the original picture again. So go take a look.